This video deals with statics and capacitors. So what happens is you get an electric field between two parallel plates, which you already know. One plate is positive, one plate is negative, so there's a change in charge, so there's a potential difference. Okay? That electric field is equal to the potential difference between the two plates divided by the distance, and it's the negative value of that. Okay, so that's your electric field. Two parallel plates is an example of a capacitor. Capacitors hold charge. Okay, they hold charge for later use. One example of a capacitor is a flash in a camera. Especially old-fashioned cameras, they needed to take time to charge their flash, and you used to hear the whirring sound coming up. Okay, it's because that capacitor is gathering and gathering and holding charge, and it holds it for later on to release it. Now, the capacitance is the measure of how good that is at storing charge. So the symbol for capacitance is C, and its units is Faradays with a capital F. A lot of times you see capacitance in terms of micro or nano, so times 10 to the negative 6th or times 10 to the negative 9th Faradays. Faradays is, makes it very small. Now, parallel plate capacitors are the type of capacitors with two parallel plates. And that's what we look at most in physics here. Now, to find its capacitance, so to find out how good it is at storing charge, how much of that charge is it going to hold? How good is it? You have a constant, E naught, which is in your reference table as 8.85 times 10 to the negative 12th, times the area of the plates. We're going to make both our plates the same area for this. Okay, the area of the plates in meters squared, divided by the distance between them in meters. Okay, so how far apart they are, how big they are, and a constant is what determines its capacitance. Now, capacitance also equals Q divided by V. Okay, so that's like its possible capacitance, and we can link it to its charge divided by the potential difference. So it's the charge of the plates divided by the potential difference between them. So if we looked back here, we saw there was a potential difference between them, and there was a charge on each plate. So these two equations are nicely linked. This is in your reference table, as is this. Well, if it's going to hold charge, then it's going to be able to do work, right? Your flash on your camera does work. The capacitor gathers a charge and does work. Bing! Flash. Okay? So in order to do work, it has to have a change in energy. So it needs to have energy. The energy of the capacitor is 1/2 QV, or 1/2 CV squared. And basically, this is kind of like the idea of power. C equals Q over V, so V equals Q over C. So if you took 1/2 Q and plugged in for V, Q over C, you would get 1/2 Q squared divided by C. If you were to say get rid of Q, because this equation doesn't have Q, Q equals C times V. So you get 1/2. We're getting rid of Q, so we have C times V times V. So 1/2 CV squared. Alright, so these are the same equations, just different variables. Let's look at an example. Two plates of 6 microfarads. So C equals 6 times 10 to the negative 6 Faradays. Are separated by a distance of 0.07 meters. If the capacitor can store an energy of 0.03 joules, determine the area of the plate, the charge stored by the capacitor, the potential difference, and the energy given to an alpha particle. So if we have U equals 1/2 QV, and C equals Q over V, and C also equals epsilon A over D. Now we know we're looking for area, and we know capacitance, we know the constant, and we know the distance. So A equals C times D divided by epsilon naught. Plug in our values. Remember the constant, 8.85 times 10 to the negative 12, and you get 4.746 times 10 to the 16th meters squared. The next question asks about the charge stored on the capacitor. Now, this is going to get a little bit trickier, because if you look at it, all of our equations with charge, they have potential difference. They have V involved. Right? We don't see anything where V is not involved. Which means that all of our equations are going to have two unknowns, or we're going to have to find V first. And all the V equations also have... Nope, they don't all have. Oh, look. Here's a V equation that does not have Q. So we can find V. So U equals 1/2 CV squared, where 0.03 equals 1/2 6 times 10 to the negative 6 V squared, and V equals 100 volts. Alright, so I'm going to erase so I have space to work on the next part. Alright, so now we're looking for Q. We have U, we have V, we can find Q. 0.03 equals 1/2 Q times 100. Q equals 6. Okay, multiply that up, you get 0.06 times 100, you get 6. So Q is 6, we got that done. We've got the potential difference across, and the energy given to an alpha particle that is accelerated across it. So change in energy. Now this goes back to last lesson. And last lesson, we looked at this. Okay, so the energy of an alpha particle that accelerated across it. So we know our V, and we're looking for our change in energy, how much energy we got. So now all we need to know is the charge of an alpha particle. Now an alpha particle is a helium nucleus emitted by some radioactive substances originally at ray. Alright, so a helium nucleus has 2 protons. So we're looking at something with 2 protons. Okay, so the charge would equal 2 times 1.6 times 10 to the negative 19th. And U equals K. Oh, well, it does equal that too, but we're interested in the QV. So U equals 2 times 1.6 times 10 to the negative 19th times v, which was 100. So we get 3.2 times 10 to the negative 17th. All right. That's all for the lesson. Good luck on your homework.